Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll continue the section B topical MCQ or section 9.4, which is on nitrogen and sulfur chemistry. So this overlaps with environmental chemistry, which is quite commonly asked in A-level chemistry, whether you are in AS or A2 paper actually. So there are four options to this MCQ. So A, B, C to D, and option A refers to all three statements being relevant to what they are asking. 1 and 2 is for option B, 2 and 3 is for option C, and if only one is relevant to what they're asking, then there's option D. Alright, so let's get started with this first question. We have modern cars fitted with catalytic converters. We know this catalytic converter uses heterogeneous catalyst. Alright, so the definition of heterogeneous versus homogeneous catalysts are required under rate of reaction topic as part of your learning objective. So these typically involve rhodium, palladium, platinum. So these are really expensive precious metals. These are solids. Most of the things that passes through a catalytic converter are gases. Alright, you can't exhaust fume, they are gases. These catalysts in the solid phase are in a different phase or different state than your reactant gases. Alright, therefore they are called heterogeneous. So this remove carbon monoxide, unburned hydrocarbon, as well as oxides of nitrogen. Which of these pollutant gases are removed by oxidation? Okay, so they specifically tell you what you remove already, but they want in terms of oxidation. So if we think about option 2 first, the hydrocarbon, you know you can write a general equation for the combustion of hydrocarbon, compound containing carbon and hydrogen atom only. You can come up with the algebra expression if you do some algebra balancing of equation. So X number of carbon will give you X CO2, Y number of carbon to get Y number of hydrogen, you need Y over 2 times 2 will give you Y number of hydrogen. We know it will give complete combustion products. That's how we come up with the X and the Y in this ratio. After you do all that, then you work out what is the total number of oxygen atoms you need, and then you can get the expression in terms of algebra. So these are most helpful when you do combustion analysis back in topic 1, which is to do with comparing stoichiometry or reacting volumes or the volume of products formed. Alright, well, I can tell you straight away, when you combust something completely, you remove all the carbon from the hydrogen, you remove the hydrogen from the carbon, so all of these carbon get oxidized. So this gets oxidized because each of the carbon then lose all the hydrogen and gain oxygen. And that's how in the context of organic chemistry, that's how we think of oxidation. So this thing does get oxidized. Number 2 is correct. In terms of number 1, your carbon monoxide gets converted to carbon dioxide by oxidation in the catalytic converter as well. So just plus half O2. So that gets oxidized because there is carbon plus 2 oxidation state. There is carbon plus 4. The oxygen as an element is oxygen 0. In the compound there's oxygen minus 2. But anyway, we're looking at carbon plus 2 becoming carbon plus 4. So the CO does get oxidized. Alright. How about oxides of nitrogen? So in the case of just this particular oxide of nitrogen, I'm just looking at one particular example. There are many oxides of nitrogen here. So in oxide of nitrogen, the nitrogen is plus 2. When you add it with CO in the catalytic converter, you will get N2 plus CO2. So this is a classic reaction, even from your O-level or GCSE days. You need to balance that with half N2, to balance out the number of nitrogen. So nitrogen in the molecule is nitrogen 0, and the carbon, as mentioned previously, is what I've just written down. So that going to that is a decrease in oxidation number. Alright, because when you go higher, you're going to get to more oxide of nitrogen. Whereas you want to go to molecular nitrogen, which is present in our air, which is much cleaner than this, because this is present in our air, we breathe it in, we don't do anything with it in our body. But this thing can cause breathing problem for us, it can cause acid rain, it can cause many things. Alright. So that is reduction, that is not oxidation when this oxide of nitrogen become the cleaner product. So 3 is incorrect. If 1 and 2 are correct, that's option B. In this next question, so we're talking about eutrophication. Eutrophication, which is a commonly asked essay back in GCSE, back in O-level, and even in AS level when it comes out it's worth 3 marks, 2 marks like that, alright? But this is essentially the first step leading to eutrophications, and then the final result is that the aquatic plants will die. They are all the fishes and the other animals as well, right? So we're talking about the nitrates. Okay, it's the nitrates. Okay, we are talking about the nitrates that really promote the excessive growth of algae. I don't know exactly how you pronounce it, but anyway, whichever one you like to pronounce them with, pronounce them as, that will be alright. Okay, so it's to do with the nitrate and not to do with the potassium or the sulfate. Of course, all potassium salts are soluble as well, so they get washed down, but it's the nitrate that causes you the excessive growth of the river plants as well as the algae or algae. Alright, so there's option C there. This next question is not contact process, it's like Claus process. That's like Santa Claus kind of Claus. What do we have? We have H2S converted into solid sulfur, which is then removed. So it's two-step reaction. Is it two-step reaction? No, it's a different reaction, right? Reaction 1 convert to SO2. Reaction 2, oh yeah, it is two-step reaction because the SO2 from reaction 1 gets converted in reaction 2 to give you sulfur. Alright, so this is basically an oxidation state kind of question. The H2S, the molecule has no overall oxidation state, so it's 0, there's no charge. The hydrogen, you have 2 of them, each of which is +1. The sulfur is therefore what you want to find, there's a -2. When you have SO2, if you don't know yet, there's sulfur +4, as you have needed to know from your standard CAT study of oxides of the period 3 elements. Anyway, the molecule have no charge, so there's 0 equal to sulfur +2 times -2. The sulfur is +4. I've just shown it there. Sulfur as an element. Okay, so as an element, the oxidation state of an element is just 0. So looking at all that, SO2 oxidizes H2S in reaction 2. In reaction 2, you have sulfur +4 becomes sulfur 0. So sulfur +4 to 0, that is a decrease in oxidation number. That's called reduction. So that reduction is being carried out by this. Okay, hang on, I got it the other way around. They don't want that. They want what happened to the H2S. Alright, what happened to the H2S? From -2 in H2S to 0 in sulfur solid, there is an increase in oxidation number. So that's called oxidation. This is being carried out by this species. So the SO2 oxidizes this to this, and that is in fact oxidation. It's being carried out by this. So SO2 oxidizes that. In reaction 2 is correct. Because it's acting as an oxidizing agent, its surface is reduced, as you see, from +4 to 0 because there's no other sulfur species. +4 to 0 is a reduction. Its surface is reduced because it acts as an oxidizing agent. In reaction 1, if I check statement 1, in reaction 1, H2S is oxidized. Well, sulfur is -2 there, sulfur is +4 there. So -2 to +4 is an increase in oxidation number. So that is called oxidation. H2S is oxidized to SO2 in reaction 1. Alright? SO2 behave as a catalyst. Well, reaction 1 produces SO2, reaction 2 uses SO2 and form the sulfur. Overall, you go from H2S to sulfur solid. That is your main reaction, H2S to sulfur solid. The SO2 is produced as an intermediate and then it's used up again. So SO2 is acting as a catalyst, alright? Or if you think about reaction 2 first, it uses the SO2, but then no, I can't think of reaction 2 first, but I can definitely tell you the SO2 is just an intermediate in the reaction, so it's some sort of catalyst intermediate. Okay, so it does help you in this reaction. So we are not told exactly, right, like SO2 increases the rate of reaction. We are simply told that H2S get converted to solid sulfur. which are involved in these two reactions. So as I mentioned, SO2 is produced as an intermediate product here, which is further converted into the sulfur here, but there is no information whatsoever that tells us about the rate at all. So we can't really say it behave as a catalyst, all right, because we don't even get it back at the end. It's an intermediate in the reaction, but it's not a catalyst because we don't get it back in the end, because we don't even start with it in the very beginning, all right. So 3 is not relevant to whatever we are interested in, so it's just 1 and 2, which is option B. In this next question, so we know that nitrogen and oxygen can react at very high temperature, one place of which is in the hot car engine, and you can get oxide of nitrogen. The other occurrence is when you have lightning. So when you have lightning, that bolt of electricity has enough energy to break the nitrogen-nitrogen triple bond, and for the nitrogen in the atmosphere, in the air, to react with oxygen to give you oxide of nitrogen. Okay, but they do not react at room temperature. As I mentioned, the nitrogen-nitrogen triple bond, very high in energy, very strong bond to be broken, very high activation energy. Okay, so number 2 is definitely correct. The reaction is endothermic. So it said do not react at room temperature. Okay, so why does it help to explain it? Well, you need high temperature, you need hot car engine. So the fact is endothermic, a higher temperature would make it more feasible and would make it more likely to happen. All right, so I guess this thing already explains the high bond energy of the nitrogen molecule as well as the resulting high activation energy. So all 3 of them are correct and relevant to whatever they're asking. Okay, this is the last question of this 5-question series on nitrogen and sulfur. So which mixtures on heating can produce the deuterium derivative of ammonia? So deuterium is just an isotope of hydrogen. So we know that when we have a test for ammonium ion, so when we test for it, we add in a hydroxide and then we will produce NH3 and H2O. So this is the most common reactions in your practical chemistry that you would definitely have done. All right, you add sodium hydroxide to something, I don't know, a solution, you heat it, you get ammonia, and you know that there's ammonium present. Okay, when you test for the ammonia with red litmus paper, moist red litmus paper or damp red litmus paper, it will turn blue as a result of this alkaline gas. When we have option 2, what we have is we have a nitrile hydrolysis. We have a nitrile hydrolysis under alkaline condition. All right, so when we have nitrile hydrolysis, so CH3CN plus Na plus OD minus, okay, and you do this in D2O, and of course you need to reflux it for your hydrolysis of nitriles. We know that we will get CH3COOD. The reason why you don't get OH is because you're using NaOD and you are in the presence of D2O, okay, but this is also acidic and you're in alkaline condition, so you will actually get the salt, okay, instead of the actual acid. All right, and then what happened to the nitrogen in the nitriles in hydrolysis, okay, is that nitrogen would actually be given out as ammonia. Okay, but in the case of this, like I said, there is no proton lying around. There is just the deuterium, which is the equivalent of the proton, because here is just completely D2O, this is NaOD, so you will get ND3. All right, as a result of your hydrolysis of your nitrile. Okay, so perhaps I should write D2O there, and you can see the equation balance out. The COO and A, and then you get the ND3 because the D there goes to the D3. This equation is balanced. All right, so you do get ND3 in reaction 2. This is a nitrile hydrolysis. A lot of students know about this product, but they never thought about the other product as well. Okay, as in what happened to the nitrogen. The first one is your classic test for ammonium ion, but in this case you have OH minus, because you have a base in a water, whereas here is solid and solid. Well, it's not a big problem when you have a solid and a solid. Let me start by thinking about the NH4Cl first, because that's the easy one to think about. You will also give out NH3, and then what's the other one you give out? You get a salt, CaCl2, and what's the other one you give out? H2O, I think. Yep, should be. Which means we need to balance the equation. 2 of these, and does that balance out? Yeah, I think that's balanced out. 1 calcium, 2 chlorine, 2 nitrogen, 8 hydrogen. So 6 hydrogen plus 2 is 8 hydrogen, 1 oxygen. Alright, so you do give you the ammonia gas, but we are not interested in NH, we are interested in D. So we get ND3, and we will not get H2O, we'll get D2O, because there's no hydrogen in here, there's just deuterium. Okay, that's the way to think about this kind of question. When it looks difficult, it might not be that difficult at all. Alright, the next bit is think NH4Cl. Alright, so I'm going to do the exact same thing. So this is your hydroxide, this is in D2O. So when I have NH4Cl plus NaOH, I will get NH3, I will get NaCl, and I'll get H2O. That equation should be balanced, because this is a NaCl, whereas previously it was calcium chloride. The NH4 will give you the NH3, one of the H goes here, one of the H goes there, you get H2O. The Na and the Cl forms that, so that's alright. So what I'm going to do now is, I will make this into NH3, and I'll have D. ND. Alright, what happened then? And then this is also OD. So we remove that and become OD. And you could potentially get that. And you could potentially get D2O. But also, okay, how can you govern that you definitely get NH3, that you definitely just lose the D there? You could also get NH2D, and then you could also get DHO. Instead of 2 deuterium, you can get D and H. And of course, you can also have two of the hydrogen there as well. Alright, I mean, you get various combinations. And what do they want? They want ND3. They want ND3, 3 deuterium, right? 3 deuterium. I'll tell you that's impossible, because you only have 1 deuterium and 2 deuterium. You only have 2 deuterium. How can you get ND3? You started from this equation which was balanced. Everything is 1 to 1 when it was NH4Cl, NaOH, NH3, NaCl, and H2O. Then you count, then you make them into the deuterium. You have this much deuterium, and in that equation you only have 1 and 2. There's no way for you to get 3 in that final product, which is what they want. Okay, so it's impossible mathematically in terms of the balance equation, and therefore it's impossible here. So it's just option 1 and 2. Alright, this is quite a tricky question if you don't think carefully about it. So this is the end of this 5-question tutorial. If you enjoyed the tutorial, click the button on the bottom right, subscribe to the channel, share the channel widely with friends, group chats, and your social network, so that you can help more people and more students in need can access these materials on my channel. Alright, thank you for sharing, and thank you for watching. See you in the next video.